Good morning, children. We started this chapter in the Zoom class yesterday. We're going to continue the same chapter. Let's make a quick recap of all that we studied yesterday. So, refraction definition goes like this: bending of or change in direction of light when it passes from one transparent medium to another. And then there are three cases. When a light travels from rarer to denser, the ray bends towards the normal. Then when the light ray travels from denser to rarer, it bends away from the normal. It goes like this. And then if a ray of incident is incident along the normal, that is, if angle of incidence is 0, then angle of refraction is also equal to 0. So these are the three cases that we saw. Then we saw about the cause of refraction. The main cause is because the speed of light changes is different in different medium. In rarer medium, the speed is more, and in denser medium, speed of light is less. So that's the reason for the bending. Then we studied about laws of refraction. So first law says incident ray, refracted ray, and the normal all lie in the same plane. At the point of incidence, all lie in the same plane. Second, ratio of sine of angle of incidence to sine of angle of refraction is constant for a given pair of media or pair of given media. That is, mathematically, sin I by sin R is equal to constant. And this law is called Snell's law. And this gives the refractive index. Okay, so this ratio of sin I by sin R gives the refractive index of a medium. Okay, so that's the definition here. Refractive index of a second medium with respect to the first medium is defined as ratio of sine of angle of incidence in the first medium to sine of angle of refraction in the second medium. Now, what is the need for writing mu 2 1 or 1 2 like that? So we are taking this as medium 1, this as medium 2. We don't know whether it is rarer or denser. Let's take generally light is traveling from medium 1 to medium 2. Okay, so suppose let us assume this is rarer and this is denser. So what happens? The ray will bend towards the normal. So this is your incident ray, this is your refracted ray. Now I can find the ray is now traveling from medium 1 into medium 2. So this will give me the refractive index of this medium with respect to this medium. The medium into which it goes, okay, and here the medium from which it comes. And when we say like this: refractive index of second medium, the right number first, means of this one with respect to this one. Okay, refractive index of the second medium into which the light is going with respect to the medium from where it came. So that's the meaning of saying refractive index of mu 2 1. Means it is going from medium 1 to medium 2, and it will give you the refractive index of medium 2 with respect to medium 1. So this will be, so sin I, this is I and this is R. So sin I by sin R is called the refractive index. That's the definition of refractive index, or this can be called as Snell's law. They can ask you in any way. Okay, then we saw about this one: effect on speed, wavelength, frequency due to refraction. So I made you note this little table. So denser to rarer, rarer to denser. Frequency will always remain the same. Frequency will not change. So time will also not change. So remember this always. When light travels from one medium to another, frequency will not change. So no change, no change. Okay. When it compares to speed of light, from in denser to rarer, it increases. So wavelength also increases. Whereas Rarer to denser, speed of light decreases and wavelength also decreases. So this is what is given in this whole paragraph. So this whole paragraph, it is given there. Then the definition of refractive index. Okay. Now we go to another definition of refractive index. This is one definition. There is another definition. Okay, this is definition number 1 you can take. This is based on angle of incidence and angle of refraction. Okay, now there's another definition for refractive index that is based on, suppose, assume that this medium is air and this medium is any medium. Okay, in the sense the light is traveling from air, that's a rarer medium, into any denser medium, can be water or glass or anything. So refractive index of medium, okay, so refractive index is equal to speed of sound. The other formula is speed of sound in air upon speed of sound in the medium. Okay, children. So we are considering light is traveling from air into another denser medium, and in this case refractive index, what you get will be the refractive index of medium with respect to air. Refractive index of medium with respect to air, speed of sound in air, this will be in the numerator, upon speed of sound in the medium, that comes in the denominator. So this is also another formula for refractive index, and this one is specifically called absolute refractive index. Absolute refractive index, in the sense, if refractive in if one medium is air, if the light ray is traveling from air, one medium is air, from air it is traveling into any other medium, then it gives us something called absolute refractive index. In the sense, numerator you'll always have speed of sound in air, that's given a special name called absolute refractive index. Okay, so you can underline this. Refractive index of a medium is also defined as, okay, you can write also defined as ratio of speed of light in vacuum or air to the speed of light in that medium, to the speed of light in that medium, and that's called absolute refractive index. Mu is equal to speed of light in vacuum or air upon speed of light in that medium. Usually speed of light in air is given, represented by c, small c, and speed of light in medium is v. Okay, so this is the symbol they use. And then here comes a reasoning question. Absolute refractive index. Absolute refractive index value will always be greater than 1. Be greater than 1. Okay, absolute refractive index will always be greater than 1. That's a conclusion. Then there is a reason for it. Why? You know that speed of sound in air is the maximum. So it's like 3 into 10 power 8. Speed of, sorry, we are talking about sound, we are talking about light. Sorry children, it's light. Speed of light in air is the maximum. You know that it's maximum in air or vacuum, and that value is 3 into 10 power 8. Okay, now suppose if we take this as glass, this medium, if I'm taking it as glass, speed of light in glass is 2 into 10 power 8. Okay, in air it is 3 into 10 power 8, in glass it is 2 into 10 power 8. So 3 by 2, 1.5. So refractive index of, what I get will be refractive index of glass with respect to air. Refractive index of glass with respect to air will be 1.5. Okay, so absolute refractive index means if the first medium is air and the second medium is something else which is denser than this, definitely the refractive index will be greater than 1. Okay, so that's a reasoning question. The refractive index of a transparent medium is always greater than 1. It can never be less than 1. Okay, the reason is given there. Okay, there's another possible question here. what do you mean by the statement? If I tell you, suppose I tell you a statement, I'm making a statement like this: refractive index of glass is 1.5. What do you mean by this statement? What do you mean? What does it imply, or what idea does it give you? Okay, so we know that refractive index is what? Speed of light in air upon speed of light in medium. It's equal to 1.5. So here our medium is glass. So I can conclude like this: speed of light in air is 1.5 times the speed of light in glass. This is the conclusion that I can get. Okay, speed of light in air is 1.5 times more than speed of light in glass. Okay, this is more, of course, so that way. So anything, if they ask you what do you mean by the statement refractive index of diamond is 2.4, okay, same way, so it means speed of light in air upon speed of light in diamond is equal to 2.4. That means speed of light in air is 2.4 times speed of light in diamond. That's the conclusion that I get. Speed of light is 2.4 times faster in air than in diamond. That's the conclusion. So this is also one question that they ask. What do you mean by the statement refractive index of diamond is 2.41? The answer is, it means that light travels in air 2.41 times faster than in diamond. Since speed of light in air is 3 into 10 power 8, the speed of light in diamond is 1.245 into 10 power 8 meter per second. Now, this table gives you the refractive index of some common substances. So, you have to remember few of them. Vacuum and air, you know, 1. Okay, vacuum and air refractive index is 1. Water, 1.33. You have to remember this. Water's refractive index is 1.33. Ordinary glass. Okay, the glasses have different varieties. This is ordinary glass, that is 1.5. Then diamond is 2.4. Diamond's refractive index is the maximum. Diamond has the highest refractive index. That's the reason why it shines like what we say, it sparkles. No? So this is the thing. Okay, so just put tick mark on these 5 readings. This alone you remember, that's enough. Now, what does this formula say? It's not necessary that always the first medium has to be air and the second medium has to be any other medium. It can be any other 2 mediums. Suppose light is coming from glass and it is entering into water. Okay, so these both are different mediums. Air is not involved in this case. So it's coming from glass entering into water. So in this case, refractive index of water, okay, usually, so if let's take this is medium 1, this is medium 2. So refractive index of medium 2 with respect to medium 1 will be speed of light in medium 1 upon speed of light in medium 2. That is speed of light in glass upon speed of light in water. So what I'm trying to say is, it's not necessary that always air should be there. If air is there, then it's given a specific name called absolute refractive index. Is it clear? And that only will always be greater than 1. Whereas this refractive index can be less than 1 also. That depends on the speeds of both the medium. So this is just a general thing when light travels from medium 1 to medium 2. And this is given a name called relative refractive index. Relative refractive index. Okay. Okay, children. Next topic. Conditions for a light ray to pass undeviated on refraction. Okay. So one thing is the third case. Whenever ray of light is incident along the normal, it is going to go undeviated. That is, angle of incidence is 0. So angle of refraction will also be equal to 0. So the first case for the ray of light to pass undeviated will be when angle of incidence at the boundary of two media is 0, as shown in figure. Okay, then angle of refraction is also 0. That's the first case. The other possible thing is when the refractive index of medium 2 is the same as that of refractive index of medium 1. If the refractive index of both the mediums are same, then refraction is not possible. Now this is possible only if both are air or both are water or both are thing. Okay, so this is a theoretical thing. When refractive index of medium 2 is same as that of medium 1, then no refraction will take place. Okay, so you can gently strike off this with a pencil, not with a pen. This is not there. Now, there is something called principle of reversibility. Principle of reversibility. Just the conclusion is important, children. Now, suppose this is glass and this is water. So, what you get is refractive index of water with respect to glass, right? Now, suppose if refractive index of water with respect to glass is, I'm just guessing, okay, I'm not sure, 2 by 3. Okay, so the value of it is 2 by 3. Then refractive index of glass with respect to water, that is, light is going from this into this. Earlier light was coming from glass entering into water. Now we are taking light is going from water, incident ray is here and the refracted ray is there. In that case it will be inverse of this, that is 3 by 2. 3 by 2. Okay, so this is called principle of reversibility. Generally they say refractive index of medium 2 with respect to medium 1 is equal to 1 upon refractive index of medium 1 with respect to medium 2. Okay, this is called principle of reversibility. So there is a derivation and all that, but you just understand this conclusion, that is enough. Okay. Then this part, experimental verification to be done practically. So you can just write practicals here. So this will be doing practically later. Now come to the last part, refraction of light through a rectangular glass block. Refraction through a rectangular glass block. Okay. So you all know what is a rectangular glass block, right? It's a rectangular, a thick thing. It's a three-dimensional thing, something like a book. It has a length, breadth and depth also, and it's a thick glass slab. Okay, now how will refraction take place in this? This medium is air, this medium is glass, and this medium is air. We are going to consider light entering from air to glass and then going out from glass into air. We are going to consider both. Okay. Now let this be our incident ray. Okay. Normal. And here it is rarer to denser because air to glass. So the ray will bend towards the normal. So it will go like this. So you always put your original path with dotted line, then bend it. Okay, then this line should be between this and this somewhere. Okay, so this is your angle I and this is your angle R. So let's name it ABC. So AB is your incident ray, BC refracted ray. Okay, then angle I, angle of incidence, angle R, angle of refraction. Okay, so it's fine. Now it's reached here. Again, there is a change in medium. From glass, it has to enter into air. So again, at this point, you draw a normal. Okay, normal has to be roughly at 90 degree. Please make a line properly. Then the ray should have, so this originally the path is like this. It should have gone like this, but it will go like this, away from the normal, because it is denser to rarer. So you get another ray called emergent ray. This ray CD is called emergent ray. The ray that emerges out of the glass block is called emergent ray. And this angle is called angle E, angle of emergence. Angle of emergence. Okay, so this is the simple diagram for refraction through a glass slab. Now, one thing you should understand, if you extend this original ray, okay, keep extending it, you will find that the emergent ray will be parallel to this extended incident ray. In a glass block, the emergent ray will be parallel to this extended incident ray. These both will keep going parallel. Okay, and the perpendicular distance between them. Okay, note the word perpendicular. That means at a point I draw a line which makes 90 degree with that. That's called perpendicular distance, because like this, if I measure, it will be a different distance. Like this, it will be different. So I'm taking this distance, the perpendicular distance between these two lines, that is emergent ray and extended incident ray. Now this is given a special name called lateral displacement. This is given a special name called lateral displacement. Okay, so sometimes we write like this. Angle of deviation is also like that. So lateral displacement, I don't think they have used anything. Okay, they've just taken as xy. So xy, lateral displacement. Hope you understood. There is no angle deviation. You know, parallel lines never meet. Means there is no angle deviation between them. They're going to go parallel, but just there is a slight lateral displacement. Now, you have the definition for lateral displacement here. So this diagram is very important with all the labelings and other thing. Then you have the definition for lateral displacement. Define the perpendicular distance between the path of emergent ray and the direction of incident ray is called lateral displacement. Path of emergent ray and the direction of incident ray is called lateral displacement. The word perpendicular distance is important. Don't forget it. Then, factors affecting lateral displacement. Okay, there are three factors affecting: thickness of block, angle of incidence, and refractive index. Thickness of block, angle of incidence, refractive index, and all the three directly proportional. Now, the reason you need not know, because there is a formula here which you'll be studying in higher classes. So, for now, you just remember these are the three factors affecting thickness of block, angle of incidence, and refractive index, and all three affects directly. Okay, so this is not in the syllabus. Multiple images is not in the syllabus, so you can strike it off. For homework, for today's homework, I want you to try question number 13, question number 25. Okay, listen carefully. Same thing. This answer is there. For something else, you can just use the same concept. What do you understand by the statement refractive index of glass is 1.5? Okay, then this is based on rectangular glass slab. The diagram for the rectangular glass slab. Okay, so 25, 26. This is also based on rectangular glass slab. Complete the path till it comes out of the slab. Mark angle of incidence, all that. The same diagram they have asked in so much subparts. Then 27 also. Okay, 27 also. So they have given the angles. This is 45, this is 30. So you have to find the refractive index. Sin 45 by sin 30. You know the values of those, and then you have to find. Okay, children. So the homework for today are 13, 25, 26, 27. The same rule. You have to finish it and send it to my WhatsApp before today. So today night. Okay, send it positively by today night. Thank you so much.